Hey guys, so I'm going to give you a very abbreviated and cut down version of the graduate level of the protein function lecture. So really what I want to communicate is that proteins can be broken down into two different categories. You can break them down to enzymes, which as a protein is going to bind to something and then is going to change that thing and then release it. Or the other proteins, which is the case that we're going to be studying today in this lecture, which is a protein that binds to other things and then just releases them after a while for whatever reason. And that thing that it binds to could be another protein or a small molecule. There's all sorts of different things. Like for instance, there are some of these which carry and transport ions and small molecules, such as the example we're going to look at today of myoglobin and hemoglobin. But all sorts of things, muscle contraction, antibodies are going to bind, but ultimately may not even release. So there's a whole range of different things to look at. So when we look at this expression, we can think of this as being back to what we were talking about with equilibriums, where you have something that comes together and it reacts to form a product, but then it's in equilibrium and it can go backwards and forwards, and is thus described by the kind of the balance at which it sits is described by the K. So these are reversible reactions. They are in equilibrium, so they're going to be balanced wherever that may be, and the balance may be 1 to 1,000. And even though that isn't equal, it doesn't matter, just as long as it is balanced. Or it may be 1,000 to 1. Which is suggesting that it favors the reactants and doesn't really want to form products. But it doesn't matter, as long as it's in balance for that particular reaction, then that is where it's going to be. And we can measure which side it's on, which one it prefers, by K. And K can be just quantified and calculated just by looking at the concentration of the products and divide that by the concentration of reactants. And think about it. If you've got a lot of product and not very much reactant, that's suggesting that the reaction is going forwards to the right. And thus the P number is going to be high, the R number is going to be low, and so K overall will be high and greater than 1. On the other hand, if you have a small P, a small concentration of product, and a large R, a large concentration of reactant, that's suggesting you've got more on this side. And thus the reaction is more over to the left. And if you had that, then you'd have a small p, a large R, then K is going to be small and less than 1. So we can say whether or not the reaction favors the products or reactants given by the K value. If it's greater than 1 and the bigger the number, the more it favors the products. If it's less than 1 and the smaller the number, the more it favors reactants instead. And in the example that we have here, it is just where PL is the products and P and L are the reactants, where P is the protein, L is the ligand, and PL is the protein-ligand complex together. And they're going to come together and break apart, and a lot of that can be dictated by the chemical situation, the chemical environment in which the protein-ligand or the protein-ligand complex are in. And a lot of this is dictated by Le Chatelier's principle. Remember that if something is in equilibrium and something happens to upset that equilibrium, Le Chatelier's principle says that a reaction will move to get back in line with where the equilibrium should sit. For example, if you have, like this top example, where you have a 1 to 1,000 ratio of product and reactant to product, and let's say it's, 1 millimolar to 1,000 millimolar or something like that, and that's just where it likes to sit. Well, if you were to add more protein plus ligand or reactants, then that is going to, if you add more, then that is going to increase what you have on this side, and that's not going to be in balance anymore. It's not going to be 1 to 1,000 anymore. It's going to be 2 to 1,000 or 1 in 500. And so it's going to work, and some of this is going to break down and turn into product to compensate for that to get back into line. And it could work in the other way even. If you were to have, if it wants to be in a 1 to 1,000, but let's say that you increase some of the protein-ligand complex, let's say you just drop some into solution, that's going to say, well, that's 1 to 2,000, although it favors the, although it always favors the products, 1 to 2,000 is favoring the products too much. And so Le Chatelier's principle say, well, actually break down and go in this direction to compensate for that. And if this is sounding a little bit strange for you, go back and re-look over some notes and look over another video just to refresh your memory on Le Chatelier's principle and the way that when things are in equilibrium, if you increase one of the things on one of the side of the equilibrium, it's out of balance and it's going to shift to get back into balance, either pushing the reaction forwards or pulling the reaction backwards. Now, like I said, we can describe this as being P plus L give the protein ligand complex, and this is going to sit in equilibrium. And we can say that along the top, the rate of it coming together, that's the K value, and it's coming together as an association. And we give that the constant, the symbol Ka. That's not Ka's in the acid Ka, they're just reusing Ka. It just means the K of association. And in a roundabout way, it's providing a measurement of the affinity the ligand has for the protein. Because if the Ka value is high, that's a high K value, then of course that's suggesting that they're going to come together. And they're going to come together because there is a strong association pushing the reaction to the right. And again, this can be measured simply by the concentration of the products divided by the concentration of the reactants. On the other hand, we can also look at it from the reverse direction. And often we do look at it from the reverse direction. I'm actually going to skip forward a little bit. We actually do look at it from the reverse way, where it's going to be protein plus ligand coming together to form the protein-ligand complex. And sometimes we look at it actually to say, well, how much does it break apart instead? When we have the complex, how much does it break apart? And we give that by the Kd, the dissociation constant, and it's literally just the reverse of the Ka. It's just 1 over Ka will give you the Kd. It literally just means the reverse, where a high Ka, remember that means it comes together more, a high Kd means it breaks apart more. A low Ka means it's not apart as much. A low Kd means it's together more. So they mean the opposite of each other. And we often use that in biochemistry. We often describe things with the Kd value instead of the Ka value, and we calculate it in the opposite way that we calculate the Ka. So instead of it being products over reactants, instead it's reactants over products. And that will give us the Kd value. This stuff here is just a smaller case K, and that's referring to rate. And that's just saying that the rate of it breaking apart divided by the rate of it breaking down. And rate is different from constant, in that rate you can think of it as being how fast is the car moving, whereas constant is where is the position of that car on the particular road at that one moment in time. So that's a kind of different kind of measurement. You know, distance and speed are two different things that are related to each other. And in the same way, constant with a K and rate with a little k, lowercase k, are related but slightly different. But for this abbreviated version, we can largely just ignore that and just concentrate on this. I'm going to go back to where I was before. Now, in a biological system, you're usually going to have a lot more ligands than you are protein. You're going to have a lot more oxygen in your body than you are hemoglobin. There's a lot more molecules of oxygen than there are molecules of hemoglobin. So because of that, it'd be quite handy to work out at different concentrations of ligand, how full does the protein get? And if you think about it, if you supply the protein with more ligand, it's going to get more full. If you take away some of that ligand, it's going to struggle to get full. And so we measure that often. We use the symbol Y, or I've often seen it with the symbol theta instead. And it's just really a measurement of percentage full. And it's just going to be how full it is divided by the total. And you can kind of think of that as being your grade is given by the points you got divided by the points you got plus the points you didn't get, which is going to be the total. The total number of points on the exam are the total that you got plus, the amount that you got plus the amount that you didn't get. That's going to be the total points. And so percentages and ratios are just given by what you've got divided by the total. So the fullness of the protein is the concentration of the full protein divided by how much protein there could possibly be to be filled up. And that is given by this equation here. And we can actually rearrange that equation, and there's a bunch of algebra that shows it in the textbook. And we can say that the fullness of the protein can be calculated at different concentrations of ligand as the ligand concentration divided by the ligand concentration plus the inverse of Ka. And remember, the inverse of Ka is also Kd, which I believe is coming up in a couple of slides here, where this is that equation saying that as you supply with more protein, the fullness of the protein goes up. Whereas if you would take away some protein, the protein fullness would go down instead. And if we just swap out 1 over Ka for Kd, then it becomes this. And what it's reflecting is that the protein is going to get more full if you supply it with more things to fill it. That's all it is. But you have to factor in the fact that sometimes it's going to break apart as well. There's a tendency for the protein to break apart. It doesn't just hold on to things forever. If it just held on to things forever, then whatever you put in is going to stay in. But because it breaks apart as well, you have to compensate for that. You have to compensate for the fact that the protein is losing its grip as well. And the way I like to think of it is using this bucket analogy. Whereas on the left, it's just a simple version if you didn't have the Kd. If you didn't have the Kd, then the fullness is just going to be equal to L. And if you've got a bucket and you put water into that bucket, then the bucket is going to fill up. And the more water you put in the bucket, the more it gets full. The faster you fill up, the faster the flow of water, the faster the bucket will fill up. And in this case, the water is the ligand and the bucket is the protein. And when the bucket is in the water, that's kind of a protein-ligand complex. And so, yeah, if you supply more ligand, the bucket, protein-ligand complex, or the protein, gets more full, forming a water-bucket complex in a roundabout way. The reality of the fact is, remember that proteins don't indefinitely hold on to things. They also break apart. Hemoglobin would be no good if it just held on to oxygen. It needs to let go of it to deliver it too. And so I kind of think of it as being holes in the bucket, where the bucket is letting go of the ligand, and if the hole is bigger, that means it has a weaker grip, and if the hole is smaller, it has a stronger grip, because if it's able to hold on to its ligand more, then it's not going to be leaking out as much. Whereas if it's holding on to its ligand less, it's going to be leaking out more. And think of it this way. If you have a bucket that's got holes in it, and you're trying to fill up that bucket despite there being holes in it, well, it's going to be, if you want to fill up that bucket, you're just going to have to supply it with more water to fill it. If the bucket is emptying faster than it's filling, well, you're going to have to just turn up the flow of water if you want to fill it up. And that's what this is reflecting here, this equation. If you want to fill up your bucket, but it's constantly emptying, then you're going to need to supply it with more water in order to fill it up. Now, if you're trying to fill up your protein, but your protein has a tendency to break down, which all proteins, not break down, the complex wants to break down, which all ligands do, then the more it wants to break down, the more ligand you're going to have to supply it to fill it up. But if it's got a tight grip, then it's going to be not that bad. If it's got a loose grip, then it's going to be harder to fill it up. And this is still dictated by Le Chatelier's principle, where you have that protein and ligand complex, protein and ligand, which forms a protein-ligand complex. And you have the Kd value, and the Kd value is kind of saying, well, is it more on this side, or is it more on that side? Is it more on the reactant side, or is it more on the product side? And to what extent? And if the Kd value is quite high, then it's going to be pushing it over to this side. But remember Le Chatelier's principle, if I increase the concentration of ligand, then I'm going to push the reaction to the right, and I'm gaining more protein-ligand complex, which is fullness of protein. So as I supply more ligand, like I say, if I supply more ligand, despite the protein wanting to empty up, it is going to get more full. And the same with the bucket analogy. If I supply more water, although the bucket is emptying, I'm going to get more bucket water complex if I increase it. and pushing the reaction to the right and forming more complex. And as with all equations, we can plot them on the graph. And we show it like this. Remember I said the y. Y is the theta, the fullness of the protein. So this is fullness. 1 is completely full, 0.5 is half full, 0 is empty. This is fullness of protein on the y-axis, and I think that's why it's given as a y. But along on the x-axis is concentration of ligand, which is increasing in amount. And it has this hyperbolic curve where it accelerates rapidly at first, but then it starts to slow down as the protein gets more full. And the KD value can be calculated by, not defined. The definition of the KD value is the dissociation constant, and it describes the extent to which the protein ligand complex breaks down. So it's not defined by what I'm about to say, but it can be quantified by the amount of ligand required to half fill the protein. That will give the KD value, but that's not the definition of the KD value. The definition is the dissociation constant. That's just a way of quantifying it, a way of giving it a number, a way of giving it a number. Now I'm going to move over to hemoglobin. I'm going to give the example of hemoglobin. Now hemoglobin is a way for oxygen to be carried in the blood. Oxygen doesn't dissolve in the blood very well because oxygen is non-polar, but blood is polar. But oxygen does bind to iron ions really well. The problem is that iron ions, they would just float around and they'd be difficult to control. But if we get that iron ion and chelate it, hold it, bite down within a heme molecule, which is a cofactor that sits inside a globin. And globin is a family of proteins. And there's a bunch of these globins, but we're going to be looking at one, hemoglobin. But there's a whole bunch of globins, and we're going to use an example, myoglobin, as an example later too. Now, this is the structure of heme here, and you can see the iron ion sits in the middle, chelated by 4 coordinate bonds. It belongs to the family of porphyrins. This is a porphyrin ring. An iron will be chelated by 4 coordinate bonds in plane with the heme, but also 1 above and 1 below, for a total of 6 coordinate bonds. The one in front and the one below, and if you can see there's going to be 1, 2, 3, 4, there's a comma between them, 1, 2, 3, 4, there's the 4 coordinate bonds, and this is the heme, and you're looking at it side on. Instead of face on, side on, and then from the top and bottom, or front and back, whichever way you want to look at it, there's this proximal histidine residue that refers to a histidine amino acid of the globin protein. Remember, the hemoglobin, the heme sits inside a globin protein. And that's coordinate bond 5, and coordinate bond 6 is the oxygen binding region. Now, that doesn't necessarily always bind to oxygen, it can bind to other things, but that is where the oxygen would bind. And so the protein is like this, and the oxygen comes in and binds in here to form the 6th coordinate bond with iron. And it kind of looks like this. Again, if we're looking at the porphyrin ring, the heme, side on this time, you can see that the iron is in coordination with these 4 nitrogens, and then you have the proximal histidine sitting behind it, and then oxygen comes in here and then binds. Now we're giving away a little hint about what's coming here. This dotted line and the cross, the cross signifies where the iron would sit if it was in plane. This dotted line and the angle of these is kind of suggesting what's coming up, that the iron can go in and out of plane. And if you think of the porphyrin ring we're looking at side on, the iron can sit here, but it can also be pulled back and sit here instead and be in or out of plane of the heme ring. And that's important because that controls its affinity for oxygen. It has a high affinity when it's in plane and a low affinity when it's out of plane. We'll come on to a little bit more of that later. Well, let's look at the structure of hemoglobin. Globins are a family of proteins They're characterized by having these 8 alpha helixes. They're connected by these bends. The alpha helixes are named from A to H for 1 to 8. And then the bends between them are named after the 2 helixes that they connect. So A and B helixes are connected by the AB bend. And the globins are really for transporting and storing things, particularly oxygen actually, but not all. There's some that do not. And it's you can kind of think of it as being a little nest in which the heme sits inside, and there's the ion. There's the proximal his. So you've got 4 coordinate bonds here, the 5th one here, and then the 6th one is where oxygen can come in and bind, or alternatively this distal his, which is when there isn't an oxygen bound, which we'll talk about a little bit later. Now, like I said, there's a whole bunch of different globins. Myoglobin, myo is in muscles, hemoglobin is in blood, neuroglobin is in neuro in the brain, and cytoglobin is something else to do with muscles. We can just largely ignore cytoglobin, but I just add it for completeness. And neuroglobin and myoglobin are actually very similar, but one's in the muscles and one is in the neurons. And really they have 2 functions in that they like to hold on to oxygen and they like to hold on to oxygen. They don't really want to let go of it. So they are useful for a really good emergency storage, but also to facilitate the diffusion out of the blood and into the cells. That is helped out by these myoglobin and neuroglobin to help it diffuse through. But the main one we're going to be talking about is hemoglobin, where hemoglobin is nice because it grabs, but then it also lets go. And the different chemical environments dictate when it will grab and when it will let go. It grabs in the lungs, it lets go at the muscles, at the tissues, at the brain, wherever it needs to let go, because it's no good if it just holds on, it also needs to let go. Myoglobin and neuroglobin are good for just holding on and holding on for an emergency. Hemoglobin, you don't want to wait till an emergency, you just want to be able to let go. One of the key things is that myoglobin is monomeric. That means that it's just one globin protein on its own. Same with neuroglobin. Hemoglobin is different in that it's tetrameric, which means that it is 4 globin proteins stuck together to make a quaternary superstructure. Now, a little bit more background. We're going to talk about myoglobin first of all. Myoglobin is very similar to one of these globin subunits of hemoglobin. It's different, but it has a lot of similarity, particularly in shape that we'll come on to in a minute. But we can use myoglobin as a little bit of a case study. It's got 153 residues, 153 amino acids, and within that sits 1 molecule of heme. 1 molecule of heme binds to 1 oxygen. In the proximal histidine is often referred to as histidine number 93, because it's the 93rd amino acid in the sequence, going from the N-terminal to the C-terminal. It's also sometimes called F8 because in helix F it is amino acid 8. Now, if we go back to the equation that we had before, the ligand is oxygen, and so we can just feed it into the equation that looks like this. And also, you remember the Kd is the concentration of oxygen required to half fill, the Kd can be calculated, quantified, not defined, calculated or quantified by the amount of ligand required to half fill the protein. And so this concentration required to half fill is substituted in for Kd in this case. Now, here you've got concentration of ligand, and they've just done it by square brackets O2. Thing is that oxygen is a gas, and so it's hard to measure the concentration of a gas in a liquid. One way in which we can do it, and is often done in the clinic and in the hospitals, is using an ABG, which is an arterial blood gas, instrument, which can measure the pressure of the various gases such as oxygen and CO2 that might be dissolved in your blood. And from that, the pressure can calculate the concentration using Henry's law. And Henry's law is that the amount of dissolved gas in a liquid, so the concentration, is proportional to the partial pressure above the liquid. And I kind of think of it as being, when you've got a can of Pepsi, is got a high concentration of CO2 in the liquid, and there's a tiny amount of gas at the top of the can, and so that gas will be at high pressure, and so the concentration of the gas will be at a high concentration. When you open that can, the pressure is released, and thus the concentration of CO2 slowly starts to decrease over time as the CO2 equalizes with the environment around it. And that is given by Henry's law. And so, just to mention, if you ever work clinically, you may see that it's not given as square brackets O2, because it's not necessarily the concentration of O2, rather it's the partial pressure O2, which is proportional to the concentration, and we can consider it effectively, for all intents and purposes, for this presentation as the concentration of O2, but it's also kind of not. But I just thought I'd mention that as a side. Now, another aside that is really important I mention is going back to some structural stuff. And remember this distal histidine that is on this side, which is the O2 binding side. Now, O2 is the only thing that can bind the hemoglobin. And in fact, several things can bind the hemoglobin, but O2 is not the only thing that will bind to iron. Remember, this ion really likes to bind to transition metals in general. This ion really likes to bind to oxygen, but also bind to other things, such as CO, carbon monoxide. And that's going to be no good, because while it's bound to CO, it's not bound to oxygen. We don't want that. We want it to be bound to oxygen. We don't want to be blocked by binding to CO. That will cause suffocation. We don't want that. So the problem we have is that carbon monoxide is a similar size and shape to oxygen. So it can bind in the same binding site and bind to that ion. It'll come into the same area and bind to that ion. In fact, actually, carbon monoxide actually binds better than O2 to pure heme. Just if you were in a test tube, just had some heme, not hemoglobin, then the carbon monoxide will bind about 10 million times better. It actually has a higher affinity for iron. So how do we solve that problem? Because otherwise we have CO binding instead of O2, and then we're not going to be able to kind of transport around O2 because it's going to be too busy bound to CO. So the solution is that the protein pocket decreases the affinity for carbon monoxide about 1,000-fold. Still binds better than oxygen, but I mean that 1,000-fold really gives you a fighting chance because the concentration of CO is much lower than O2. So we can live with that, we can tolerate that. But if it didn't, then even very minor levels of CO would cause suffocation. But because CO levels are low enough, and with the additive effect of the protein pocket decreasing the affinity for CO, that together makes it so that you can tolerate the normal atmospheric level of CO. Now, if it rises, then it becomes a problem, but atmospherically and normally it becomes fine. And CO is highly toxic because it competes with oxygen and various heme compounds, not just hemoglobin actually, of course, the same will be with myoglobin, but also the mitochondrial cytochromes involved in oxidative phosphorylation that contain heme groups. Because as you can see here, heme will bind to CO, carbon monoxide, will bind to heme, and while it's done that, oxygen won't be able to bind. But what you may be able to see and so you won't be able to transport your oxygen or do whatever it is that you need to do with oxygen. But what you may notice is, you see this oxygen is at an angle, this carbon monoxide is straight. That's actually really significant. They've not drawn that by coincidence. And if we look at the structure of the protein, we can see that here is our heme, and here's our proximal histidine coming in behind it, and here's our O2 in front, and it doesn't binding to the front of the iron for the coordinate bond number 6. And notice that it doesn't bind straight on, instead it binds at an angle. And that's no coincidence, or rather, I mean, it's always going to, O2 is always, let me change pen color. O2 is always going to bind to iron and heme at this kind of angle. That's always going to happen. Nature takes advantage of that. The distal histidine will help to doesn't know, but rather the protein has evolved so that the distal histidine is in the position so that it will actually stabilize the second oxygen atom of the O2 molecule in order to increase the affinity for oxygen. If this wasn't here, then you'd only have one thing binding to oxygen, but now you have two things binding to the oxygen. So it helps increase the affinity for the oxygen here. but also it changes the shape of the pocket. And so something does not want to fit up here. It's sterically blocked. So not only does the distal histidine electrostatically stabilize the iron-oxygen complex, but it also sterically hinders the CO from binding, because the CO would bind like this, and it kind of blocks. So the shape of the protein binding pocket helps to block CO and improve binding for O2. Now let's go back a little bit more to the math again, and remember this graph from before. If I increase the concentration of ligand, I'm going to increase the fullness of the protein. In this case, we're talking about myoglobin, and it's got this hyperbolic curve. Now, the problem with this is that you can see that the protein becomes full very quickly. Only 2 kilopascals of oxygen. It's already like, I don't know, 95% full, something like that. And the problem is that 2 is a fairly low, is a pretty low concentration of oxygen. The 2 kilopascals of oxygen is bordering on hypoxia, which is oxygen starvation. And so the thing is, if we go back to our equation, protein plus ligand forms a protein-ligand complex, and that is, the extent to which that breaks down is the Kd. Now the Kd is very low, and so the Kd is very low. That's reflecting that myoglobin has got a very strong grip on the protein, and so at very low concentrations of, and so remember, if Kd is low, it's going to push it more to the right, and saying that it's associated more, which means at a low concentration of oxygen, you're going to have this protein-ligand complex. The problem is that means that it's not really, it's going to stay as the protein-ligand complex and not break down to release oxygen. Excuse me. And so it's not actually, if, remember Le Chatelier's principle, if the concentration of ligand decreases, so we're saying that we enter into very low concentration of ligand, which is kind of reflecting hypoxia, then yes, okay, eventually complex is going to break down in order to release some ligand, which is oxygen, but it won't do so until the concentration of ligand drops down really low in order to push Le Chatelier's principle to the left, because the Kd is so is also pretty low. So it's all the way over on it's pushing it all the way over to this side. It's not breaking apart. And so that's no good. You're only going to release oxygen when you need to in an absolute emergency. So that's going to be a little bit of a problem. And hemoglobin can't have that problem, because if it did, then it would. If it had that problem, then it would be able to release the oxygen. It would just hold on to oxygen and not let it go. And so what we need to do is that we need to lower the affinity. We need to actually change the Kd value to make it so that it will let go of the oxygen. And so what it can actually do is that hemoglobin can change affinity, so that it has a sigmoidal curve, and so it will have a high affinity for oxygen in the lungs. So it will get full up quite readily at the site of the lungs, where you have a high concentration of oxygen. So it will get quite full up. But then at the lower concentration of oxygen, and let's say tissues, a healthy amount of is probably actually around about let's see here, it's kind of regular oxygen thirsty. Well, it's going to be 50% empty at the site of the tissues, whereas myoglobin is only 5% empty, 95% full, and so it's only releasing 5% of its oxygen under regular conditions. It doesn't become more empty until you start getting into hypoxia conditions around about here. But hemoglobin doesn't have that problem. It is able, if it was just a curve like this, then it wouldn't get very full. And sure, it would get very empty, but it wouldn't get very full. By having this sigmoidal curve, it has a Kd value that changes. So the Kd value is low here and high here, in order to pick up oxygen and get really full, or drop off oxygen and get really empty here. And this is largely to do with the 3D conformation. The 3D shape of the protein will change in order to change into a conformation that has a low KD and a high KD. And this is that whole thing of structure equals function. The chemistry causes the hemoglobin to change, protein structure to change, and when the protein structure changes, it changes from a high KD to a low KD, or a low KD to a high KD. And that's dictated by the chemical environment. So if in the case of myoglobin, it doesn't take much oxygen in order to fill it up. So if L is high, then it'll push the equilibrium to PL. In fact, L only needs to be very medium, moderate, in order to push the equilibrium to PL. So myoglobin will easily carry oxygen. But it does mean that the oxygen needs to drop very low before it will release, because if L is low, then it'll push the equilibrium by Le Chatelier's principle to P plus L, and L is oxygen. So it's letting go of ligand, it's breaking apart. So it will only break apart when Le Chatelier's principle dictates that the L drops down low enough in order to push it over to the left. Now, like I said, the trick in this is that there's a key difference between myoglobin and hemoglobin, which will cause this to happen. And this is related to the structure equals function. There's a difference in structure, which is causing a difference in function between oxygen grabbing and oxygen letting go. Myoglobin and hemoglobin, as you can see, are fairly similar. To the eye, they look fairly similar. The difference, though, remember, is that hemoglobin is tetrameric. It has 2 alpha chains and 2 beta chains that make up the tetrameric protein. Remember, those alpha chains and the beta chains are protomers, 2 protomers, and each one carries 1 heme group for a total of 4 heme groups. And if we were to look at the structure of hemoglobin, if we look at the sequence, blue has shown similarity, white has shown dissimilarity. We can see that there's not a ton of similarity, but there is a lot of structural similarity, where if we overlay several globins, they're very, very different. So actually the individual globins are actually very similar. It's, I mean, the sequence similarity is not uncommon in families where there's a low sequence similarity, because a valine and a leucine, for example, could belong to the same family, and they're probably going to lead they're a different sequence, but they may lead to the same structure because they're similar things. But you see that the tertiary structure is largely similar. So the difference between hemoglobin and myoglobin is likely not to be due to the tertiary structure. Rather, it must be due to the interaction between the individual tertiary structures that overall make the quaternary structure. And between these subunits, the alpha and the beta subunits, between them there is going to be the interface. That's where they touch. There's interfaces. That's where they touch. I've drawn in red. And these are keeping them together by various forces: the hydrophobic effect, hydrogen bonds and ion pairs, ionic attraction, salt bridges. And between the alpha 1 and the beta 1 subunit, this interface here has about 30 amino acids which are touching, that have these forces keeping it together as a pair. But also between the alpha 1 and the beta 2, for example, here, this interface here, there's 19 amino acids which are keeping that together by these intermolecular forces. But these subunits can slide. They slide past each other. When they slide past each other, it gives these interactions can break and change into different ones. And when they do, the protein moves and changes shape. And so maybe it is shaped like, I'll start here. Maybe it's shaped like this, first of all, but then it moves and it's shaped like this instead. They slide and they change in order to give a different shape. And that different shape, that's when the KD changes. Maybe it might be a low KD, and then this has a high KD. We're going to talk a little bit about how that happens. Now, those 2 different conformations are referred to the R state and the T state. The R state stands for relaxed, and the T state stands for tense. And that's just the way that they decided to name them. There is a reason for it. It's not the most intuitive, but there is a reason for it that we'll come on to in a moment. The R state has a high affinity for hemoglobin. The T state has a low affinity for hemoglobin. And it's the predominant conformation of deoxy, as in there is no oxygen hemoglobin. And you can see there's a few subtle differences between these proteins. One of the key ones is the donut hole. The donut hole is larger in the R state. But there is a few differences that we're going to talk about in a little bit. The structural differences that cause these different changes. The R state is going to be more as PL, and the T state is going to be more as P. Okay, so these are R and T above and below, and then this is T and R, which is above and below. So it's a little confusing. It's correct. I should probably just put the T above so it lines up with this, and the R below so it lines up with this. In the R state, it's going to be more in the PL, and in the T state, it's going to be P plus L, so it's empty and has released its ligand, which is O2. Now, if we were to represent that in a graph, if we had pure hemoglobin in the R state, it's going to look like this. And like this, well, here's the concentration of ligand to remember, and this is the concentration of ligand in the peachy colour in the site of the lungs, so it's much higher in the lungs, of course, and so the protein is full. Problem is that at the site of the tissues, where the concentration is lower, the protein is full in the R state. And we don't like that because it's just going to be PL. There's not going to be any P plus L, remembering that L is O2, so there's not going to be any oxygen, which we want. That's the problem. Now the protein in the T state, at the site of the lungs, the concentration of oxygen is such that, remember if we do P plus L, it gives the protein ligand complex. Now in the T state, the KD value is making it so that it favors this side more. We've got a high KD value which is favoring this side. But if you add enough oxygen as ligand, then you're increasing this side, and so Le Chatelier's principle, you're going to increase this. And so what you see is that at the higher concentration, you do get an amount of protein ligand complex. If you decrease the concentration, such as you see in the tissues, where there's not as much oxygen because you're using it and you're not breathing through your muscles and things, the concentration is lower. Because the concentration of ligand is lower, then it's going to be able to push the equation, the concentration of ligand is lower, that's going to push it to break up and move over to the left, and thus replace that ligand, and this is breaking up, and it's releasing that ligand that comes off as O2. Now the whole thing with that is that the difference between this point and this point is, let's say, I don't know, what's that, 20, let's say it's about 28%. Okay, that means that when the protein is full, it gets to maybe let's say 48%. When the protein is empty, it gets to about 20% full, which means it's released about 28% oxygen. If you had when it's in the site of the lungs, it might be 48 millimoles of PL, but in the site of the tissues, it's going to be 20. I've butchered the math here a little bit. I haven't, no. It's going to be 20 millimolar PL plus 28 millimolar O2, because it's P O2, which is L. So it's going to maybe between in the lungs, it may be about 48, but in the tissues, well, it's going to be only down to 20, which means that the 28 that there was before is released as oxygen. So it's going to be like that instead. I guess it would be more like 28 PL plus 20L plus 20P. But that's much of a muchness. The point is that as it moves into a lower concentration state, the complex is going to break apart and releasing oxygen. Whereas that doesn't happen in the R state. But what we do find in reality is that the protein is going to be in it's never going to be completely in the R state or the T state. The protein itself is in an equilibrium between the R and the T, where different factors can come in. They're going to push it from one side to the other. That's the chemical environment. But it's never 100% going to be in the R and the T. Some of your hemoglobin is going to be in the R, some of it's going to be in T, especially in the whole of your body, and in any particular localization. So what we actually see is this hybrid where it gets almost full in the site of the lungs when it's in the R state, and then it gets that didn't come out quite so well, and then it gets a little bit more empty in the site of the tissues, where there's a lower concentration of oxygen. It's going to put Le Chassier's principle, push it to the left, thus into protein plus ligand, where ligand is O2, releasing that oxygen. And so it's going to get maybe about 97% full in the site of the lungs, and about 60% full at the site of the tissues. So it's released about 37% oxygen. So it's kind of like having a car that you fill it up to 97% full, and you drive it to 60% full, and then you fill it back up to 97. Then you drive it to 60, then you fill it back up to 97, and you go and you keep going like that. I guess in a roundabout, fairly morbid factor is that as you run out of gas, you're kind of releasing CO2 in the example of the car, and that's the 37% that's being released. Except in the case of hemoglobin, it's the PL, and the concentration of PL decreases, and thus the concentration of L is increased, and L in this case is O2 instead. Now, what causes that conformational change is various things binding to hemoglobin. I'm going to talk about a little bit more of them later, but in effect, if we start at the T state, that's in the deoxy, O2 absent state, oxygen is going to bind to that, and oxygen is going to bind to it and induce it to change into the R state. So it's going to be at the site of the lungs. It's going to be in the T state, and it's going to return to the lungs, and then the concentration of oxygen in the lungs is going to push it into the R state and get it to fill up again. And then it's going to travel to the tissues, and then the chemical environment of the tissues and the low concentration of oxygen is going to push it into the T state, which is going to then get it to release its oxygen. So as it comes back to the tissues, as it comes back to the lungs, it's in the T state, and the concentration, the high concentration of O2, although it doesn't want to bind to any O2, because the concentration is so high, Le Chassier's principle is going to push it to the right and generate PL complex, and so it's going to have to take on some O2. And when that happens, what that does, it causes a structural change. This is that change in the chemical environment. The chemical environment of the lungs is such that it has a high concentration of oxygen, and that is going to, the chemical environment is going to cause the subunits to slide past each other and rotate. Some ion pairs stabilize the T state, that some of those that do stabilize the T state will break, and some new ones form, stabilizing the R state instead. And so the high concentration of oxygen in the lungs is, by Le Chassier's principle, is going to force itself onto the protein to form the protein ligand complex. In doing so, it will cause a structural change into the R state. Now it's in the R state, it's going to bind to oxygen better, and so the next oxygen is going to get on easier. The first oxygen is kind of tough, but the first oxygen is going to cause the change into the R state, so the rest of the oxygens go on easier. We call that the cooperative effect, where oxygen helps oxygen bind. And it's kind of like if you've got a bunch of people that are going to trying to climb over a wall, and the first person has to struggle to get over the wall, but then they lean over and help the other person get over. In the same way, the hemoglobin is in the T state, doesn't want to bind oxygen because the concentration is so high. Le Chassier's principle pushes it to the right, forces it to take onto that oxygen. Once that oxygen has bound, that will cause a change in the shape of the protein just by simply having an oxygen bound, and it's kind of moving around, pushing around. It's going to change the shape of the protein. When it changes the shape of the protein, that will that as it change, things will break, things will change, bonds will break, new ones will form that slide past each other, change into the R state, and now it's in a much more receptive shape conformation for the oxygen, where it has a low Kd value, which is going to grab onto the oxygen, and that high concentration of oxygen is going to be easy to grab onto that oxygen. And this is kind of what you see happening in the T state and within the R state. Within the T state, you have a lot of these positive charges in the center, and these are repelling each other, making it very tense, and that's where the name comes from. In the R state, these are stabilized by two histidines that are sitting in the middle. But when it moves into the T state, these histidines, they move up here. And so these histidines were down here and attracted to certain things down here, keeping them in that shape. When the chemical environment changes, that will cause the protein to change shape, and so these will move up into here and form new attractions here. So these ones will break and new ones will form. And so the histidine HC3, so that's going to be a histidine in the helix C3, and that is, it's histidine, it's helix H, C terminal 3. So 3 amino acids away from the C terminal on helix H is going to move into a different position, and so there's a lot of positive charges now in the center, which are repelling each other. And this, which is kind of explained by this text here. And you can identify those histidines here. Now, what this has the effect of doing is that when the whole protein changes shape, that proximal histidine here is going to be normally pulling on the ion in the heme in plane, and in the R state, where it's more receptive, that proximal histidine is keeping the ion in plane, where it combines to oxygen freely. But in the T state, the shape of the protein changes, and it pulls the ion back, and now the oxygen falls off because the ion doesn't have such a close grip on it. Now, these things that can bind to hemoglobin, that can affect the way that hemoglobin, the function of hemoglobin from a high binding to a low binding, we call these modulators. And that we can break it down. Modulators, ligands that binds to a protein to induce a conformational change and thus change the function. And there's a few different types of these. Now, these don't bind in the active site, rather they bind outside the active site, and that refers to what allosteric means. Allosteric just means that something binds outside of the ligand binding site to influence the ligand binding. So ligand 2 binds to the protein outside of the ligand 1 binding site to influence the binding of ligand 1. And the classic example is that when you breathe, when you respire, you produce a lot of CO2. And so there's going to be a lot of CO2 in the areas that need oxygen, because that's where the respiration is going on. So the CO2 will bind to hemoglobin outside of the oxygen binding site, but influence oxygen binding to decrease the oxygen binding to release the oxygen. And thus CO2 is allosteric. Now, there's a few different types of allosteric modulators. There's the homotrophic and heterotrophic. Heterotrophic is that example I just gave of CO2. Homotrophic is where the ligand and the modulator are the same thing. Now, let's start out, first of all, nice and simple. Let's just start with a monomeric protein. And let's say that we've got a monomeric protein and something binds here. Everywhere outside of that is allosteric to the active site. So if something binds here and changes the binding here, then that is allosteric modulation. It may be positive or negative, depending on it increases binding or decreases binding. Now the thing is that in hemoglobin, you've got the 4 subunits, and you've got the 4 hemes where 4 oxygens bind. Remember I said that oxygen binding helps other oxygen bind. And so the first oxygen may bind here, and may make it easier for the oxygen to bind here, here, and here. Now because these 3 sites, although they're oxygen binding sites, they are not this oxygen binding site. And so these are all allosteric of it. And so oxygen is a homotrophic positive modulator, because oxygen binding at site number 1 increases oxygen binding at site number 2, 3, and 4. And because oxygen and oxygen are the same thing, they are homotrophic. Because they're modulating, they're modulators. Because it's outside of the same site, they are allosteric. And because it increases, it is positive modulation. CO2 is released by respiring tissues. It binds the hemoglobin, causes a change from the R into the T state, and that causes the affinity for oxygen to decrease. The Kd increases, and thus it is a heterotrophic negative allosteric modulator. There are a few different things that can bind to hemoglobin, and some of the classic ones are CO2 and acid protons, which comes from lactic acid, which comes from respiring tissues. And so the end products of cellular respiration, protons from lactic acid and CO2, signaling that there's respiration going on here, they bind the hemoglobin to push it into the T state, acting as negative allosteric heterotrophic modulators. The binding of H2, H plus, and CO2 are inversely related to the binding of CO2, cause it to release. This is called the Bohr effect. The Bohr effect is that decreasing pH, increasing CO2 cause the release of oxygen into from hemoglobin. And you can kind of see it by this graph here, where we can see that at a high pH, saying that there is less acid, then let's say that a concentration of 4 kilopascals, the protein is, I don't know, 75% full. But at more acidic concentration, it is about 45% full. So you see that difference is that it's not able to hold on to as much oxygen when the pH is lower. And CO2 will do exactly the same thing, where CO2 will bind to hemoglobin and will stimulate the changing of the shape into the T conformation, and will then the T conformation is going to let go of the oxygen. It's acting as a heterotrophic modulator instead. Now, finally, one other thing that is produced by respiration is going to be this molecule BPG. BPG, 2,3-bifosphoglycerate, is a intermediate in glycolysis. And so if you've got a lot of respiration going on, you've got a lot of glycolysis going on. And so this BPG will bind to hemoglobin and also act as a heterotrophic negative modulator. Because if there's more BPG, there's more respiration, there's more of a need for oxygen. But notice these negative charges. Remember what I said earlier about the tenth state, about the donut hole. The donut hole has got all these positive charges. And so the negative charges of BPG help to stabilize and act as a counter-ion for all of these positive charges, and thus the T state can exist. If you don't have BPG, the T state can't exist because you don't have anything to stabilize these positive charges. But if you have BPG, you are allowing the T state to exist because you've got something to stabilize the positive charges that exist around the donut hole. And so you push the equilibrium actually from the R state towards the T state by adding in BPG. And this becomes important for things like altitude sickness. Now, like I said, remember that the BPG is required for the protein to exist in the T state. So without BPG, it just exists in the R state. And look at this black line here. Looks an awful lot like the R state that we looked at earlier on. But the reality is that there is BPG. BPG is just in our blood, helping to stabilize some of the hemoglobin in the T state, so it can release some oxygen. And so at around about sea level, the concentration might be around about 5 millimolar in your blood. And we have this sigmoidal curve where in the at sea level, the concentration of oxygen is around about here, kind of, I don't know, like 13-ish kilopascals, the concentration of oxygen in the lungs, and thus in the normal hemoglobin, which is given by the blue line, gets about 97% full, and then when it gets down to the tissues, let's say it's 98% full, makes the math easier. Gets about 98% full at 5 millimolar BPG. Because there is some BPG, can't get 100% full, but 98, pretty close to 100, I'll take that. Now, what happens is that when it gets to the site of the lungs, let's say that it's about 60% full, which means that it has released about 38% of its oxygen, which we have here. Now, the problem comes is that if we stay with just the 5 millimolar concentration of BPG, but we are up in the mountains where the concentration of oxygen is lower, that means that the lungs don't get the hemoglobin doesn't get as full. And let's say that maybe it only gets about 90% full. That means that when it goes to deliver, it still only delivers as much, because the BPG level is the same, it still only delivers down to about 60% full, and thus it's only delivered about 30% oxygen, and 30% is less than 38% oxygen. That means you're going to get starved of oxygen, you have lower oxygenation, and you're going to get hypoxia. Now what happens is your body detects this lower delivery of oxygen, detects, oh, it's only getting 90% full, and it's still delivering down to 60% full, so it's only delivering 30% oxygen. That's going to be a problem. So more BPG is released into the blood as a result. And so what that means is that if we give the example now at sea level, at the higher concentration of BPG, okay, you know what, sure, the protein doesn't quite get as full. So let's say that it only gets now in green with the higher concentration of BPG. Let's say it only gets 96% full. 96 isn't quite as good as 98, but that's only 2% less. And then when it goes down to the, this is at sea level still. When it gets travels down to the tissues, the concentration of oxygen is thus that it goes down to 60%, and so now it only delivers 36% oxygen, but that's still pretty close to the 38% oxygen. So even though we've got a higher concentration of, roll that back a little bit. Let's go back to the beginning of the higher concentration of BPG. Now, it's going, because of the higher concentration of BPG, it might only get 96% full. That's still good. We're going with the green line, I apologize. That means that at the site of the tissues, because there is a higher concentration of BPG, it's going to release more oxygen. All right, it's in the T state more. And so it may mean, actually, that if you had more BPG, but it was still at the high concentration of oxygen sea level, ground level, then it might deliver here, let's say, 45% oxygen. And that only get down to 45% full. That means that it is now going to be, let's say, 51% oxygen has been delivered, which is greater than the normal 38%. And that's how a lot of doping happens, where people might get injected with BPG to simulate being up in the high altitude, and then that means that although they don't quite pick up as much oxygen, they deliver so much more that it's worth it, and they overall deliver more and can perform better at sports. Now this is okay and important when it comes to altitude sickness. Now the lower concentration of the oxygen, in the up in the mountains means that, okay, sure, overall you do take up less oxygen, but because you deliver so much more, it's worth it. That's the point. I'm going to wrap up now. Now, on the opposite side of this is fetal hemoglobin. Adult hemoglobin has got the alpha subunit and the beta subunit. Fetal hemoglobin's got a gamma subunit instead. The gamma subunit increases the Ka, decreases the Kd value. That means that maybe it's not as efficient at delivering oxygen. as we mentioned previously, but that doesn't matter because it needs to have a high Ka value in order to take oxygen from the mother. So the gamma subunit increases the affinity for oxygen. Almost done. Now we just need to mention the Hill equation. That's it. Now remember, P plus L gives the protein ligand complex. Now the thing is that as we've discovered, some proteins have got multiple ligands. And so one protein may have n ligands, which means it may form PLN different complex. And so if we rearrange that into the equation the same way as before, it will rearrange to give this equation here. The fullness of the protein is equal to the concentration of the ligand multiplied by a factor of how many different ligands can bind. But the thing is that this factorial up here is going to be modifying this. If this factorial is a big number, that's going to make it so that at a low concentration of ligand, it actually has a big effect. Whereas if this number here is less than 1, that's going to mean that it's actually having a negative effect. So positive modulators are going to be increasing n to a number greater than 1, making it so that less L is required to fill the protein. Whereas negative modulators are going to have an n value of less than 1, meaning that more L is required to fill up the protein. And so we'd like to be able to find out what n is. And so simply, we can just rearrange the equation. We can rearrange it to this, and then if we take the log of both sides, we can rearrange it to this. But now we have n isolated, and we have a y equals mx plus b plus minus b, doesn't matter, which is a straight line equation. And if we solve for n, then that will tell us whether or not a modulator is having a positive or a negative effect, requiring more or less ligands to fill the protein, and can quantify it to say the extent at which that happens. And we can plot that on a Hill plot, a plot of y versus x. And if, like I said, if n equals 1, then the L is not being affected at all. If n is greater than 1, it's saying that less L is required to fill up the protein. If n is less than 1, then it's negative cooperability. That's going to be things like CO2, BPG. That's saying that more ligand is required to fill the protein, and thus at the same ligand concentration, the protein is less full. And so if we were to plot that straight line, it would look like this. A myoglobin has got nothing that influences it. So n is just 1. So it's just a straight line. There is no slope. Or the slope is 1, rather. Now hemoglobin, remember, it can flick between the T state and the high affinity R state. When in the high affinity R state, it's steeper, and so you have it's about 3 times cooperation, meaning that 3 times less oxygen is required to fill up the protein. So so not as much is required to fill it up, so it has a higher affinity. And this is really just the same thing, like I'm saying. Remember, in the R state, that's where the n equals 3, and in the T state, where n equals 1. So that's just really very briefly what the Hill plot is, and that n is the Hill coefficient. I should mention. You've got the Hill equation, Hill plot, and n, the slope, is the Hill coefficient. If it's steeper, it's meaning that the same amount of ligand will cause more fullness, or less ligand is required to cause fullness. And then finally, sickle cell anemia, the very last thing. Sickle cell anemia is just a medical condition where the glutamic acid at position 6 has been substituted for a valine instead. Glutamic acid is polar, valine is not. That causes a hydrophobic patch, which causes the red blood cell, the hemoglobin to change, and will cause a bad conformation of the red blood cell, and it will cause actually the hemoglobin to instead to aggregate and form clumps, and it actually traps the protein in the T state. So it can't take on any oxygen. And that's everything I wanted to mention. Thanks very much, guys.